since we've missed a couple of days, we're going to talk about quadratics. Okay? What y'all have missed is this. I'm going to draw this graph of quadratics. It's going to come down. I'll draw it in a different color. This graph is going to come down and extend back up and go this way. So there's some parts of the quadratic that are different than what you've normally seen with linears. But there's some parts that are the same. For instance, this right here is the same. Where it crosses the y-axis is called the y-intercept. Okay? Where it crosses the y-axis, y'all remember that from linear. Where it crosses the x-axis is our x-intercepts, and like we talked about in our warm-ups today, we also call them roots and zeros. Alright? There's also one other key feature of this graph that's very, very important. And that's this point right here. And it's not always at the bottom, but it happens to be this time, and that is my vertex. Where that graph sort of turns on itself and starts going into another direction, that is called the vertex. And that imaginary line that goes along with it is what we call the axis of symmetry. Because if you look at the graph, when I look at it, this side looks the same as this side if it had been drawn perfectly. Okay? So we call that the axis of symmetry because that's where it's reflecting upon itself. Alright? Can everybody see that, or do I need to zoom in a little bit? Zoom in a little bit? Alright, do that. Now, some things that are different with a quadratic than a linear is that it is shaped differently. It's shaped in a U. And we call that a parabola. That is the actual term for the shape of a quadratic, a parabola. Okay? I'll zoom back out here in a second. So it's called a parabola. I'm going to see if I can get the graph in there. Alright. Also, if you look at it, a linear just goes straight across, and it continues going straight on forever and ever and ever at the same rate. We say that it has a constant rate of change, but a quadratic does not. It does not have a constant rate of change. What was the form that we are most familiar with linears when I'm writing an equation? What was the equation for linears? Y equals what? Y equals mx plus b. Quadratics is a little bit different. We can say that y is equal to ax squared plus bx plus c, where a, b, and c are numbers. Okay? For example, if I had y equals x squared plus 10x plus 24. That would be an example of a quadratic. Does that look familiar to what we've been doing in this class? Okay? The x squared plus 10x plus 24 should look very familiar. That's a polynomial. We looked at that all last unit. Okay? Like I said, all of this is going to be building upon what we already know. Some of the pieces that we used from last unit are very, very important to the things that we're going to be looking at this unit. For example, do y'all remember factoring where we took and we went from this to two binomials? We went from a trinomial to two binomials by using either the box method or factoring. Do y'all remember doing that? Okay, well, let me give you an example. What are some factors? Remember, what number do we factor when we're factoring a trinomial? This one, or this one? The last one. We're going to factor 24. Okay? So if we factor 24, we would have 1 and 24, 2 and 12, 3 and 8, and 4 and 6 as factors. And what's going to be the one that adds up to the number that we need? 4 and 6 will give us 10, 8 and 3 gives us 11, 12 and 2 gives us 14, and 1 and 24 gives us 25. So these guys are my factors, okay? Well, as it happens, I can write this and this into my calculator, and it will graph the same exact line. If I were to type in the graph feature of the Inspire, y equals x squared plus 10x plus 24 and hit enter, and then I would go back and enter x plus 4 in parentheses times x plus 4 both in parentheses, you would not see two lines because it would be the same, or you would not see two quadratics because it would be the same graph. Okay? These two things say the same exact thing in two different ways. Alright? The reason that they're both important is because these two things give us two different parts of our quadratic, both of which are huge for quadratics. When you look at this graph, first off, when I looked at linears, what were the important things for linears when we were looking at our equation? And we looked at the graph. What were the important parts? The slope was one of them, and then the y-intercept was the other part that was very, very important. With quadratics, our vertex and our two x-intercepts, or roots or zeros, are very, very important. These equations are very, very important in identifying those parts. Let's take, for example, this second equation, y equals x plus 4 times x plus 6. What do you know about x-intercepts? If I were to look at a graph of any, it doesn't matter if it's a linear or a quadratic or a cubic. If I were to look at a graph, what is true about every x-intercept? What's going to happen? Let's look at this. Well, sometimes they will touch. But what is important here and here? They are on the same level, right? Which means what? The what? Okay, let me put it a different way. if this is the origin right here, let's create an ordered pair. What is this ordered pair? Negative 1, 2, 3. Negative 3, what? 0. Let's create an ordered pair and let's round to the nearest whole number here. 1, 2, 3, 4. 5. 5, 0. So what can you tell me about these two ordered pairs? What is 0? The y value is always 0, okay? That's very important in being able to figure out what my zeros are for a quadratic. If I know that my y is always 0, when I'm looking at my x-intercepts, actually I'm going to use a different color pen because that one's dying. My x-intercepts, if you can factor it to this form right here, y equals x plus 4 times x plus 6. And remember that these numbers are always going to change. If I can factor it to that, you know that what is always going to be 0? The y. So I can substitute 0 in for y. And when I substitute 0 in, now I can break these apart and create two separate equations to where 0 is equal to x plus 4 and 0 is equal to x plus 6. And now I can start to figure out what my x's are going to be for my roots. So how can I solve this? Because I can't put x and 4 together, so I drop the parentheses, right? So how can I solve this and find out what x is? Yes, Carly. I subtract 4 from both sides, so x becomes what? Negative 4. There's one of my x-intercepts. And I can do the same thing with this equation over here. What? Where? I can subtract 6 this time though, and x will become negative 6. Okay? It's very simple if you know how to factor. The struggle that I've seen in the other classes is they have a hard time factoring and knowing which ones to use, what factors to use in order to get their trinomial. The other equation that's important is this quadratic equation right here. The x squared plus 10x plus 24. Because remember, these guys say the same thing, right? So if they say the same thing, I can use either one of them. This equation is important in finding the axis of symmetry. Okay? So in order to find the axis of symmetry, I can take and find the opposite of my b value and divide it by 2 times my a value. And I let the classes yesterday figure that out on their own. We talked about it, but in order to get where we need to be, I'm just going to tell you that that's the formula that we use to find the axis of symmetry. So if I look back at this equation, which one of these is my b value? Is it the one that's in front of the x squared? Is it the 10 that's in front of the x? Or the 24 that's by itself? Well, let's look here. Which one of those is in the same spot as that b? The 10. Okay? So I'm going to take and substitute that 10 in for b. And then I'm going to divide by 2 times, what is my a value? What number is in front of that x squared here? There's not a number, is there? So what number do we put there? 1. So it'll be 2 times 1. So I can take and make 10 opposite, so it's now negative. And take and multiply 2 times 1, so this is 2. So I'd end up with negative 10 divided by 2, which is what? Negative 5. So the axis of symmetry for this equation right here is going to be on x equals negative 5. Okay? If I look at my axis of symmetry and I look at my x-intercepts, let's put those in the frame so that you can see both of them. What do you notice about the x-intercepts and the axis of symmetry? Okay, what about negative 4, negative 5, and negative 6? Okay, well look at negative 4 and negative 5. Let's put it up here on the board. Okay? 1, 2, 3, 4, 5, 6. That's negative 6, and that's negative 4, right? Where's negative 5? Right in the stinking middle. The axis of symmetry will always fall right in the middle in between your two zeros. Every time. Okay? That's why those are important. Are there any questions over what we've gone over so far?